Introduction to cluster algebra. So let me start with a brief overview of the entire course. So it's going to be 3 lectures, as you know. And so today, in the first lecture, I want to talk about the definition and some basic properties of these cluster algebras. And then in lectures 2 and 3, I'm going to focus on the particular types of cluster algebras that have been studied thoroughly in various contexts and have their own specific combinatorics happening. So the first one's called cluster algebras from surfaces, and then the other one's called cluster algebras coming from coordinate rings of the Grassmannian. So these are what's coming on Wednesday and Friday. All right. Okay, so today we're going to start with the definition of a cluster algebra, which is going to take us some time to go through. It's somewhat involved. And so a lot of the times when you hear cluster algebras, many people don't go through the definitions. They may tell you some key properties, but because the definition is somewhat involved. So it's nice to go through it in detail in the course. Then we're going to talk about some key properties and elaborate on those. And lastly, I want to go through the classification, so nice results where we can define particular types of cluster algebras and then classify them completely. Okay, so some background or some history. So cluster algebras were introduced by Fomin and Zelevinsky in 2001, so about 20 years ago. And it's a class of commutative rings that live inside the field of rational functions on the variables x1 through xn. So these are the indeterminates, and let's say my coefficients are in Q in the rational numbers, and so the elements are just, say, polynomial divided by a polynomial in these variables x1 through xn. And why such an interest in cluster algebras? Well, because soon after the introduction, there's been numerous connections to other fields of mathematics and physics, and these have led to some really, really interesting results and on both fields and helped to prove some important conjectures outside of the world of cluster algebra. So the theory really took off, and it's been a very, very exciting development. So for example, there's lots of connection to combinatorics, and that's what mostly we're going to be talking about in this course. It's really already in the definition of cluster algebra, there's a lot of combinatorics embedded in there. There's also very, very close connections to representation theory that people study. And so in my own line of research, I study combinatorics, representation theory, and cluster algebra. So that's my little triangle. But there are also very close connections to lots of geometry, including tropical geometry, Poisson geometry, symplectic geometry. So many, many geometries. Also very interesting connections to physics and such as scattering amplitudes, BPS spectra, and things like that. Also nice, very sort of some of the new results. There are new connections to knot theory as well. And there have been various connections to number theory where you can encode some very famous sequences in terms of cluster algebra mutations. So this is just some overview to say that, yes, we're going to be learning this very small thing, but in reality, it's quite widespread. It's an interesting phenomenon that appears in other areas, even though, again, the definition, when you see it, may be quite involved. Okay, so let us start. So our basic object we're going to start with is a quiver. So quiver is just another name for a directed graph. Always, when we talk about quivers, these will be finite. So it's a finite collection of vertices and a finite collection of arrows. Now, there are 2 restrictions we need to make on the graph. So the first one is we are not allowed to have loops in the graph. So a loop is a vertex together with an arrow that starts and ends at the same vertex. So we assume we don't have any loops, and we also don't want to have any 2 cycles. So a 2 cycle is a quiver where you have these 2 vertices and you have arrows going back one direction and arrows coming back in the other direction. So these are not allowed. We are allowed to have arrows, multiple arrows between the same vertex, as long as they all go in the same direction. We don't like these cycles. Now we're going to always label, this is just for convention, always going to label the vertices 1 through n. And so these are just some examples of quivers. So that's a pretty nice quiver on 3 vertices and 2 arrows, no cycles. This is what we call a 3 cycle, 3 vertices and 3 arrows all in an oriented cycle. As I said, you're allowed to have multiple arrows in the same direction. So this is an allowed quiver. But then, I mean, as you can imagine, the more vertices you have, the more arrows you have, these can get quite complicated and can have a pretty complex structure. So, I mean, everything else is allowed. So these can be quite big. All right, so the key notion in the study of cluster algebras is the notion of a mutation. And so we're going to start with the mutation of a quiver. So given a quiver Q, mutation is a local operation on the quiver, which can be defined as follows. So we are going to start with the vertex K, some vertex of Q, and then the new mutated quiver, and we're going to denote it by mu sub K of Q. So it's a quiver obtained from our initial one by applying the following 3 steps. So there are just 3 steps in this operation. So step 1 is that whenever you have a configuration like this, so K is the vertex we mutate, this is the distinguished vertex, we've chosen to mutate it. And whenever you have an arrow from I to K, and whenever you have an arrow from K to J, so these are not paths, these are indeed arrows. So whenever you have a path of length 2 passing through vertex K, what you do is you're going to add a new arrow from I to J. So you're going to add an arrow from I to J directly, which bypasses the vertex K. Second step, you reverse the direction of all arrows which are adjacent to the vertex K. So you flip where they go, source and sink. And in our last step 3 is, well, in this operation, steps 1 and 2, you could have possibly created some 2 cycles. And we do not like 2 cycles. So we're gonna, in step 3, we're gonna remove a maximal collection of 2 cycles if there were any. So at the end, again, we're gonna have a quiver with no 2 cycles, so everything is good. So the order actually does matter here. So you wanna make sure you keep the order. Sometimes it may be defined differently, but then the order would be switched. And again, this mu K of Q, this is called the mutation of the quiver at vertex K. So this depends on the vertex you're going to mutate in. Okay, so let's go through some examples. And here's our steps 1, 2, 3 that we've seen on the previous slide. So let's say my quiver Q is this 3 cycle vertex, 1, 2, 3, 3 arrows. And let's say I want to compute mu sub 3 of Q. So I'm going to mutate at the vertex 3. Okay, all right, so let's do the steps 1, 2, 3. This is my quiver. I'm going to mutate vertex 3. So step 1 says I look at all the paths through vertex 3 and I'm going to add new arrows. So I see I just have one path from 2 to 3 to 1. That's the only path of length 2 through the vertex 3, which means in my step 1, I'm going to add a arrow from 2 to 1. So after step 1, I have the following quiver. So same as before, except now I have a new arrow from 2 to 1. In step 2, it says I'm going to reverse all arrows at the vertex 3. So here I have this one outgoing arrow and this one incoming. And after step 2, you see they switched. This one switched from outgoing to incoming. This one from incoming to 3 to outgoing. So that's my result after step 2. And after step 3, well, did I create any 2 cycles? Yes, you see between 1 and 2, there's this 2 cycle going forward, going back. So I'm just going to delete these 2 arrows and my resulting quiver is as follows, right? So you started with this quiver and after steps 1 to 3, you got into this one. So it's, okay, the number of arrows, as you can see, may change. This one had cycles, this one doesn't have cycles. So things do change, okay? You're not getting the same. All right, let's try maybe a more complicated example just to make sure we understand.
Excuse me, I have a question. It says that for every trio of IKJ, we add, no, it says that there's an arrow from I to K and there's an arrow from K to J. We add an arrow from I to J. But in the first example, we had another 3 vertices, like we can look at from 3 to 1 and then to 2.
Good. Okay, let me answer your question. Good question. So remember, when we mutate this, we mutate at a vertex. So we first choose a vertex to mutate it, and then we look at the path going through that vertex. So our vertex here that we chose is 3. That's why we only look at path from 2 going through 3, 2 to 1 to 3. Indeed, there is a path that starts at 3 and goes to 1 to 2, but we don't consider it. It would only make a difference if you were to mutate at vertex 1 instead. Does that answer your question?
Oh, yes, I didn't notice that this k is fixed in the beginning.
Yes. All
Thank
right,
you.
good question. Yes, please do ask questions. I want to go slowly to make sure we actually understand this, because I don't want to lose anybody. And if you lose you at this beginning of the definitions, then it will be difficult to keep up with the course later on. Yes, the k is sort of, you have to first choose the k we're going to mutate at. So there's a choice involved here. All right, so let's do another example. So let's say this is my starting quiver Q, and now I want to mutate at vertex 1. Okay, so there's a little bit more going on here. You have this double arrow. All right, so I start with this quiver, and let's say I mutate at 1. So in my first step, so it didn't exactly fit. So after my first step, I'm here. So here at step 1, I look at all the paths of length 2 through vertex 1. So I have this path from 3 to 1, and I have, for example, can go down to 4. So 3 to 1 to 4 is such a path, which means I'm going to add a direct arrow from 3 to 4. That's this arrow. I also see a path from 3 to 1 to 2, but actually there are 2 such paths, so every arrow will count. So I go from 3 to 1 via the top arrow. I can also go from 3 to 1 via the bottom arrow. So actually there are 2 paths from 3 to 1 to 2. So I'm going to add 2 arrows from 3 to 2. So my resulting quiver after the first step is as follows. I have 2 arrows from 3 to 2, and I added an arrow from 3 to 4. Okay. In my step 2, that's the easy one. You reverse the arrows adjacent to 1. So all of these arrows at 1 get reversed. And my step 3, well, I look at if I created any 2 cycles. And so you see here, I have 1 arrow going this way and 2 arrows going that way. And I'm going to delete these 2 cycles pairwise. So I think of this arrow and that arrow as being in a 2 cycle. So I'm going to delete these 2. But the last one still stays, and I still have a remaining arrow from 3 to 2. So you delete the 2 cycles pairwise maximally. And so we still have this arrow from 3 to 2. We have this arrow from 3 to 4. And that's my resulting quiver after mutating at vertex 1. All right, questions here?
Yeah, if we had 2 arrows going from 3 to 1, would we have to add 4 arrows from 2
Correct.
to 3?
Then we would have 4 arrows from 3 to 2. That's right. So it's with multiplicities. Yes, indeed.
Thank you.
Other questions? All right, very good. Okay, so some facts or observations that are sort of not so hard to see already from the definition or properties. So first of all, quiver Q and the mutation of the Q at the vertex K always have the same number of vertices. So the number of vertices remains the same, and that's what we want. The arrows can vary. After mutating a vertex at a quiver after mutating at a vertex, the quiver has still no loops, because first of all, we started with a quiver no loops, and we cannot make more loops. And because of step 3, there's still no 2 cycles. So at the end, we still get this nice quiver. And so this is important for the fact that once you mutated a vertex, you can keep doing mutations again and again and again and get more and more quivers, because the 2 conditions that we needed are still satisfied. Okay, part 3 says that mu k of q is a local operation. And so this is you can see from the definition is, well, the quiver only changes and cares about the vertices and arrows which start and end at vertex k, and it doesn't care about all the sort of vertices that can be further away. So it's a local operation. It changes some things near vertex k. It doesn't really do anything from far away. So property 4 maybe is not so easy to see, but that's part of one of the homework exercises. Says that if I mutate at vertex k, and then I mutate at vertex k again, so I repeat my operation, I actually get back to the exact same quiver. So this operation actually undoes itself, so that's very nice. We can undo mutations and get back to where we started. So this mutation operation is something in involution. So mutation squared is identity. And the last property says, well, if I mutate at a vertex, have a quiver, and I mutate a vertex j, and then I want to mutate a vertex I, it is generally not the same as mutating at I and then at j. Of course, okay, if you try enough examples, you'll see, okay, when exactly can I do this? So you can the two commute precisely when you don't have any arrows between I and j. If they're not connected by an arrow, then the two will commute. But in general, this is not a commuting operation. So order does indeed matter. Okay. So something that we will talk about is something of notion of an equivalence class. So we say that a quiver Q is mutation equivalent to a quiver Q prime whenever there exists a finite sequence of mutations, mu sub I, such that if I apply it to a quiver Q, I get to Q prime. Okay, and this is indeed an equivalence operation because mutation operation undoes itself. You can undo it, so it's an equivalence relation. That's right. So sometimes we will care about quivers up to this mutation equivalence. And whenever we talk about sequences of mutations, we always have them finite. They can be arbitrarily long, but we do talk about only finite sequences of mutations. And so we're going to use the notation square bracket Q to denote the set of all quivers, which are mutation equivalent to a given quiver. And so kind of the picture you want to have in mind is as follows. If you want to understand this, this mutation class. So here I start with a quiver Q, and I have, again, I always assume my quiver Q has n vertices. So I can find n quivers, which are one step away from Q via a single mutation. So I can mutate at 1 and get a new quiver. I can mutate at 2, I get this new quiver. I can mutate at 3, and so on until I can mutate at the last vertex. So I get these sort of one step away mutations from Q. And now, starting from each of these other one step away mutations, I have n further possibilities to go. So starting at this one, I can mutate at 1, but remember, mutation is an involution. So if I mutated this one at 1, I would get back to where I started. Now I could mutate it at 2, so I get a new quiver, mu2, mu1 of Q. I could mutate it at 3, and so on until I could mutate at n. So these sort of green ones, they represent 2 steps away from the one I started with, and then you keep going, okay? So this is really, this could be really big and really infinite in general. It is big and infinite. All right, and so let me just point out that actually there is no known algorithm to determine whether so I give you 2 quivers and you want to say, well, are they mutation equivalent? Does there exist a sequence of mutations which takes me from one quiver to the next? And then there's really no algorithm to determine that. We don't have an answer for this question at all. And I think that's a pretty hard problem. Plenty of people have tried it since cluster algebras have appeared. Yes, question.
Yeah, I've got a question. Are those mutations form a group on a given quiver?
Okay, so you want to group. Okay, these
well,
are
maybe not for all quivers, but maybe for some special types, or it like only like really rarely in extra special conditions, or maybe it's always.
Okay, let's see. So I mean, quiver mutations could then form a group, I guess. The identity element, you don't do anything, and every mutation is...
Is composition of mutation is again a mutation?
Indeed. Sure. I mean, you can define, you can find a group to be something that's just generated by mutations, mu1, mu2, but then it would have to be a group which depends on the quiver Q.
Well, like if our group, it should be something like direct product of something like C2 to the power n if n is number of vertices, because we've got that
Oh, actually,
But it should be not commutative. It is not commutative.
it is not
Well,
commutative, but also you have
yeah.
some strange, okay, I guess it's not really a group because okay, sometimes, for example, you can, so starting with a quiver Q, for example, I could do mu1, mu2, but then I could go some other way around and I could get back to the same quiver. And so then you have lots of relations here. But moreover, it will really depend where you're starting at. So you have to make sure that you start at Q. So sometimes you can do, like going from here to here will mean something. But if you were to start at a different spot, it would not be, it would not satisfy the same relation, which is why I don't think it is a group.
No, it is obviously a group. Transformation generate a group, but probably we don't know what it is.
Yeah, we don't know what it is, and they're complicated relations, and things get, yeah.
Could be free.
I don't think people have studied it from the point of view of a group. People studied quivers. People studied mutations that are sequences of mutations which get you back to the same quiver or to the isomorphic quiver. So you study sort of the group of automorphisms of the quiver, things like that, but haven't really looked at, I think, mutations as a group in that way.
Okay, thank you.
Yeah, so I do encourage you to really kind of try examples yourself and see what's going on. So there are some nice things that happen, but then for nice quivers, we can say some more good things that happen, but in general, I mean, things do get quite involved. And again, if you think of it, if you do want to think of it as a group, you'd have to sort of have you starting with a particular quiver Q. Yeah. Yes, but the question whether two quivers are mutation equivalent is still very, very open. Right, and now, yes, okay, I can still switch. Okay, so this is just the definition pertaining to the quiver. We have not gotten to the algebra part yet, so now we are putting in more structure to see the cluster algebra. Okay, so Q is a quiver with vertices 1 through n. Now, as I said, my cluster algebra in the beginning, A sub Q, which I'm going to denote A sub Q, it lives inside the field of rational functions on x1 through n, and it is defined by a set of generators, and the generators are called cluster variables. So this is the term I'm going to use a lot, cluster variables. And these cluster variables, they are not algebraically independent. They satisfy relations, and these relations are called exchange relations, and everything is defined recursively. So given a quiver, I can just give you complete set of relations generally and generators. There's a procedure you have to do, a mutation procedure, which generates a lot of this data. Okay, since everything's generated recursively, I have to tell you what is the initial data. So once you know the initial data and this recursion operation, then you can run the algorithm and define the rest of the information you need. So my initial data is called a seed. So a seed is going to be a collection of generators, a collection of cluster variables, which we're going to use this bold X to denote. And our initial seed is always, you start with this set of generators, x1, through xn, okay, where n is the number of vertices in the quiver. So one generator for each vertex of the quiver and your initial quiver Q. And so these are called initial cluster variables, and this is the initial cluster and the initial quiver. Okay, everything's initial. And then there is a mutation operation mu sub k. And given any seed, it's going to produce a new seed, mu sub k of xq, where I have to do some mutation of this cluster, of these cluster variables of the generators, mu k of this bold x, and the quiver mutation. So this mu k of q, this is the quiver mutation we've just gone through. So this you understand. I would just have to tell you what this mutation does on the level of variables. And then once once we have that, then actually the cluster algebra is then defined as being the algebra generated by all of the cluster variables obtained from the initial seed by sequences of mutations. So you start with the initial seed, you can mutate in any of the directions 1 through n. just like think of the previous slide, and then from there mutate again, in finite. I mean, perhaps this will, you will need sort of, this will have infinitely many generators, that's fine. And but you mutate, generate more and more variables. And once you collect all of this data, then you can find your cluster algebra. Okay, so now sort of to finish with the definition, you're sort of still in the middle. I want to tell you how to define this mutation of the variables. We know the quiver mutation, we want the variable mutation. So starting with a seed, its mutation is defined as follows. So given x, so x is not necessarily an initial seed. It has some input, some data, some functions. So f1 through fn, these are cluster variables, where these fi are functions, again, rational functions in x1 through xn. And now I'm going to define the mutation of this at the vertex k as follows. So all the functions remain the same, the ones that I started with, only the function in position k will change because I'm mutating at vertex k. So everything remains the same, but except here I'm going to have fk prime. So I'm just going to now give you the formula for fk prime. So to compute the fk prime, you take the product of all the variables fi, where for every arrow ending at vertex k in your quiver Q, and then you do the same. You take the product of the variables fj in your cluster for every arrow k, for every arrow ending from k ending at that vertex in the quiver Q. Okay, so it's you have these two monomials, you'd add them, and then at the end you're going to divide by the old variable at position k. Okay, so it's some product of things you already had plus another product of things you had before in your cluster over the old variable. And this is also an exchange relation. It tells you how the new variable is related to the old variable. So if I were to multiply by fk on both sides, I would get fk prime times fk is this sum, right? And so, all right, just remember, so then the mutation of a seed is a new state where this is the quiver mutation and this is the mutation of the variables. Okay, so let us do some examples. I think that will be very nice at this point. Okay, so suppose this is my quiver Q, the 3-cycle quiver, then let us compute the cluster variables. So my cluster algebra by definition is going to lie in the field of rational functions on the variable x1, x2, x3, because I have 3 vertices. And now my initial seed is these initial variables, x1, x2, x3, together with the initial quiver. Now, again, there is a choice of where you can start mutating. Eventually, if you want the cluster algebra, you want all the possible directions, but let's just start by mutating at vertex 1. So if I mutate at vertex 1, let's do the cluster mutation first. This means, by definition, my variables in positions 2 and 3 don't change. Only the variable in 1 changes. And what is the rule for the new variable in position 1? You look at this initial quiver. You look at the arrows going into 1. You only have 1 arrow at vertex 3, which means I'm going to take x3, the cluster variable associated to position 3. That's x3. I have a single arrow going out, and that's going to vertex 2, which means I'm going to take a single variable at this position 2, x2, and I add them and divide by the old variable in position 1, x1. So that's my new set of cluster variables. And my new quiver is, we kind of did a similar example. That was our first quiver mutation. So if this would be the quiver mutation at vertex 1, you would have created 2 cycles, but then you delete them. So that's kind of in gray. It's not really part of the quiver. This is the leftover procedure for mutation. And again, you would have to do this again. So now this is your new seed. And now let's say you want to mutate again. Let's say now you want to mutate at vertex 2. So now starting with this seed, I mutate vertex 2, which means my variables at position 1 and 3 remain the same. This is my variable at position 1, the same variable at position 3 as I had from before. And something changes in position 2. And what does it do? I have to look back at the quiver. So I mutated 2. So notice in this quiver, there's no vertices coming into that vertex. So it means I take the empty product, which is 1. So that's why there's a 1 appearing here. There's a single arrow coming in out of 2 into vertex 1, which means I'm going to look at this seed. I'm going to look the variable in position 1 here. I'm going to take it. So that's That's my product of the arrows coming out of 2. That's the product of the variables for arrows coming into 2. Divide by the old variable in position 2 here, and that's your new cluster variable. And this would be the quiver mutation. So notice actually here, 2 is a source. There are no arrows coming into a source, into here. So quiver mutation is very easy. Step 1 does nothing. Step 2 just reverses the arrows at 2. And step 3 does nothing. You've created no 2 cycles. So quiver mutation in this case is very nice. So now this is your new seed, and now you have to mutate again. And so you have to do this for all the possible directions, 1, 2, 3, and generate possibly infinitely many cluster variables in this way. So your algebra A sub q is generated by x1, x2, x3, the cluster variables, the initial cluster variables, as well as this one you got via mutation, as well as this one you got via mutation, then ... okay? Repeat the procedure, get more variables, get more relations, and so on. All right, questions here.
Could you please repeat what is Q of x1, x2, x3?
Oh, this is the field of rational functions on the variables x1, x2, x3. So the elements are polynomials in these variables divided by polynomials in these variables, with coefficients in the rational numbers. Actually,
Okay,
these will be integers even, but that's okay.
Mm-hmm.
I mean, the cluster variables will have coefficients as integers, but yeah. There's another question?
I had a question about AQ. It's all possible finite combination of mutations, right?
Yes. So you take finite mutations, but they can get arbitrarily long. So in theory, you would have infinitely many cluster variables then.
Okay, thank you.
May I ask a question, please?
Go ahead.
Is the initial seed unique, or you can change order in x1, x2, x3?
Oh, okay, good question. So I think of these as, so I label this x1 because I think of it as a cluster variable associated to vertex 1 in here, x2 associated to vertex 2. So if you were to change, sort of,
yeah,
you can change, but then you kind of want to think about what you actually want to do with it. Yeah, but yeah, does that make sense?
But
so you can change. You can change things, but again, the order, the 1, 2, 3 just means, they vertex 1 corresponds to variable 1. Yes,
well,
yes, it's not independent.
Yeah, for this graph, cycles would not matter, but like permutations,
yes,
I mean, transpositions.
Sure, yes, that will matter. But yeah, actually, that's a good point. I mean, so we chose to start with x1, x2, x3 when we talk about sort of, one can actually start, you don't have to start with x1, x2, x3. These could actually, you could think of it as some sort of possibly expressions, as long as they are algebraically independent variables in here, then you can start the cluster algebra. Then your algebra would lie inside the field of rational functions in these, whatever these variables are.
Thank you.
Yeah, I have a question. Are there some condition on graph for this subring to be proper, or it's always proper subring?
Oh, it is almost always, no, it is always proper, as we will see. Actually, I tell you better. I'll tell you in a few slides a better, it doesn't really live inside of here. It lies inside something very smaller in between here. But even then, it is not the entire thing. So yes, it is. So there's, right, if it was always the entire thing, then this would not be very interesting. And it's actually never the thing that you may think it is. It never lives inside this ambient field. It never equals this ambient field. Yeah. Okay, very good. So there's something else I want to say on definition, which will be important for the exercises and following. So the exchange graph of the cluster algebra is an n-regular graph where the vertices, they correspond to seeds, except sometimes whenever you mutate, you can get the same seed up to some permutation. So I want to identify the seeds up to permutation. So the seeds under the equivalence where the cluster variables, so these generators be the same as the collection of generators, but maybe just permuted. And then the quivers would also be the same, just again permuted according to how the variables are permuted. So so we always generally consider seeds up to this equivalence. Permuting the order and the vertices of the quiver doesn't really sort of, we can ignore that. And then the edges correspond to mutations. So in general, this thing is an n-regular tree, because that is if you have no relations at all. So where every mutation gives you a distinct seed. But you may have where a mutation at x1 and x2 is the same. For example, a mutation x2, x1, and then you identify the two. And so let's do an example. Okay, so here's quiver Q. Let's say it just has one vertex. In this case, you can complete the entire cluster algebra. So your initial seed is x1, and this is your quiver. Mutation at the quiver does nothing because you have no vertices. Mutation at vertex 1, then, well, you have no incoming arrows, you have no outgoing arrows. So this is empty product plus empty product over the old variable x1. So this is the variable 2 over x1. And actually mutation, as I said, the quiver mutation is in involution. Actually, a cluster mutation is in involution. So if I start here and I go back, I would get back this seed. So actually, in this very, very small and naive example, you have only two cluster variables, this x1 and this 2 over x1, and your cluster algebra is generated by these. Okay, so this would be actually this Laurent polynomials in the variables x1 then. Okay. Okay, another sort of smaller example, and this is the exchange graph, okay? I go back, forward, back. These are my two unique, distinct seeds. Now, sort of the second smallest example you can do is the two vertices and no arrows. And in this case, this is my quiver. Again, quivering mutation does nothing because I have no arrows. And if I mutate at vertex 1, it's really the same as mutating previous one at vertex 1. My new variable would be 2 over x1. x2 remains the same. If I were mutated at 2, I get 2 over x1 and 2 over x2. But then it's the same thing as starting with the initial seed and doing first 2 and then 1. So this is my exchange graph. So my exchange graph is this, I don't know, square or diamond, okay? So the next smallest example is where you have two vertices and a single arrow between them, and that's for homework. So to try to compute the cluster algebra in that case. And in that case, it is also finite. Yeah, so these are, here you only have finitely actually many cluster variables. So that's quite special.
Will it always be the case that it's finite? Or...
No. That's the opposite. Yeah, so we actually know precisely when it is finite, and I will indeed tell you that. All right, so this looks scary, but do not be alarmed. So there are two very important properties, sort of the properties that we will care about, and the two big results, nice big results in cluster algebra is, first is the Laurent phenomenon, which was already observed by Fomin and Zelevinsky when they introduced the cluster algebras. And it says that, well, the cluster variables you get are actually Laurent polynomials in the xi's. So this means that, yeah, so I told you generally these live inside the field of rational functions. So the numerator is a polynomial and the denominator is a polynomial. But Laurent polynomial just means that the denominator doesn't have any pluses. It's just a single term. It's a monomial. It's a single product of the xi's. All right. So, and it is really not obvious from the definition that this happens. If you just start computing, okay, so let me not go through the detailed computations here, but just go through and tell you what happens. So for example, if you start with this slightly more complicated quiver, you mutate at vertex 1, you get this variable in position 1. Then you mutate at vertex 2, you're going to get this variable in position 2. If you mutate at vertex 3, this is the new variable you get at vertex 3. And you see still, these are still, if you were to do some algebra to them, this is, and simplify, you would see that this is a Laurent polynomial because the x, right, x3, it's the same as multiplying by the numerator by 1 over x3. So the denominator would be x1, x3, x2, x3. So these are Laurent. The denominator is a monomial. But then in the next step, what you do, the new cluster variable you get, so I didn't repeat the old ones, is something like this, okay? These get quite complicated. And the miraculous thing that happens is, well, now this doesn't look like Laurent. You have this denominator here, but the sort of the nice thing that happens is that this whole thing, if you were to simplify it, do some algebra to it, it's going to factor out, and it's going to have this, one of the terms would be this, and it's going to cancel with the denominator, and it will be Laurent at the end. So there's very nice cancellation happening, that at the end, all of these are actually Laurent polynomials. So they don't live inside the field of rational functions. They actually live inside the field of Laurent polynomials in these variables. Okay, questions here?
Oh, well, like how to prove it, and
well,
is it like clone proof?
It's not actually that hard. You can look at, there's a nice book being written by Fomin and Williams. It's part of it is appearing on the archive, by chapters on cluster algebras, and then you can look in there, and they actually have a proof that you can read. It's not overly long, and it's nice, and yeah, it's actually not too bad. Yeah, I mean, this was already proved in 2001 by Fomin and Zelevinsky when they were introduced. So this was something that one could do. Now, there's another property of cluster algebra which took much, much longer to prove. You see, over 10 years. And this was known as the positivity conjecture. And it was conjectured already by Fomin and Zelevinsky, but then they weren't able to show it. And the statement says that these cluster variables actually have positive or non-negative coefficients in the variables. So, okay, maybe you're thinking, okay, I actually haven't seen any negative signs here. How can I get negative coefficients? Well, this is not obvious. Remember, if in our mutation procedure, you take a product of some positive Laurent polynomials, and divide by a positive Laurent polynomial. Well, how can I not get positive out of it? Well, it's not. Okay, so smallest example, maybe this is positive, you divide one by the other. At the end, they simplify and you actually get negative terms out. Okay, so it is not an obvious, this is by far not an obvious statement, and it took a really long time to prove it. And it was first proved for various types of cluster algebras, but at the end, Schiffler and Lee found a nice proof, uniform proof, which surprisingly didn't use any heavy machinery at all. It was just lots and lots of algebra. So lots and lots, if you want to look at that paper. Yeah. So that was a nice result. All right, so out of this, these Laurent phenomenon and positivity, they can motivate the following questions, which has sort of driven a lot of work in cluster algebras is, first of all, can we find an explicit formula for cluster variables? We don't want to be doing mutations and all of these things. It actually is quite involved. If you have more complicated quivers, as you've seen in that other example, can we get an explicit formula which doesn't use the recursions for the cluster variables? Another question as well, since we know that the coefficients are positive, these are always positive, well, natural question, and integers, what are they counting? Can we find some sort of interpretation for them? And the third one is, can we also find a nice basis for a cluster algebra, sort of a vector space basis? And I mean, usually want some nice properties for this basis. So at least you want the cluster variables to be basis elements, but then you need to actually throw in a lot more stuff. And so maybe what are the structure contents represents and so on. So these questions are like very general and they've been answered. Some of them have numerous answers depending on the type of the cluster algebra if you restrict. For the general ones, we also have some answers, but then because they are so general work, they're quite more involved. So, but there's been a lot of work in that direction. All right. So I've been talking about cluster algebras of different type, and so these are the types people have studied and are important, is that the cluster algebra is said to be of finite type if there are only finitely many cluster variables. So that's something we observe. We've seen examples of that. That's single vertex or two vertices and no arrows. Actually, two vertices and one arrow would also be of finite type, as you will see. So you will only have finitely many cluster variables. So some nice things are happening, and actually all of these, there are a lot of relations in the mutations, and then you're not getting infinitely many. Now, A sub Q, the cluster algebra is said to be a finite mutation type if the mutation class of Q is finite, meaning that if I just look at the quiver and then I mutate the quiver in all the possible directions, I only get out finitely many quivers. The number of cluster variables may be infinite, but the number of quivers may be finite. And these are still nice enough class that we know them and understand them. There's another class which is said to be acyclic, and so this one's important in representation theory when you categorify cluster algebra, so I just want to mention it. AQ is said to be acyclic if there exists a quiver in the mutation class of Q that has no oriented cycles. So the one that, okay, and so these are also nice because there are more things that work in that case and we can understand them from more perspectives. So this is kind of a diagram which tells you how the related. So finite type is sort of the smallest one, the nicest one, finitely many cluster variables. And this one we can classify completely. These are of types A, D, and E, and I'll explain that on the next slide. And this is included in the finite mutation type. So if you have finitely many cluster variables, then you have finitely many seeds, and then you have finitely many quivers as well in those seeds. So you're a finite mutation type as well. Actually, finite type also is a cyclic type, so that's a nice intersection between the two. There's also something called tame type. So these would be not a finite type, they're infinite type, but they're still nice enough. And yeah, you know more information about them as well. And then outside of the finite mutation type and acyclic type, everything else is called wild. Pretty much everything outside of finite mutation type is also called wild. And then, I mean, wild, so meaning there's really no hope in trying to understand all the cluster variables in that case. Yeah. But for these, we can do some more interpretation, answer the questions 1 to 3 that we had on the previous slide. Okay, so Fomin and Zelevinsky, this, I think maybe in their second paper, showed that AQ is of finite type, so only finitely many cluster A variables if and only if the quiver Q is mutation equivalent to one of the following. So we know exactly when you're finite type, you're either mutation equivalent to this AN quiver, which is the nicest case. So it's just n vertices and all the arrows go in one direction. You're type D if you have n vertices and you have this fork at the end, exactly this, and so exactly like this. And then you're of type E6, E7, or E8 if you're something like this. So what I mean here, so these are infinite families and they, as n grows, these grow, and so you can have many vertices. Here they just work if you have 6, 7, or 8 vertices. And so E6, meaning E6 is a quiver where I can kill the vertices 7 and 8, and this would just be the E6 quiver. E7 is when I forget about the 7 vertex. E8 is when I have all the 8 vertices. And somehow if you try to think about, well, why can't I do E9? If you put a 9 here, this would be an infinite type. So things break. So it's kind of this E type is usually the exceptional type, and you don't have a family. Questions?
Is it coincidence that they are similar to, how do you call it, Coxeter graphs?
No, this was the, like, when they first saw it, this was the very beauty of it. Okay, the finite type, the Coxeter diagrams, they already appear everywhere in math. Well, this is another place where they also appear. And they actually showed that there is a bijection between the cluster variables and the roots, what do we call them? So the positive roots as well as the negative simple roots. So there's a bijection between cluster variables and positive roots of these systems, as well as the negative simples. So that's what they showed.
Other Coxeter graphs are not given such nice structure.
So there's also the non-simply laced case, and you can also do cluster algebras. So these would be called skew symmetrizable cluster algebras, and the finite type would correspond to the non-simply laced graphs as well. But then all the others would give you infinite. Yeah, this is an if and only if statement. So if you add more vertices in a non-allowed direction, that's it. You have infinitely many cluster variables. Good question.
Can one say something about the representation theory of one quiver and its mutation? Some relations or equivalence, something like that.
Well, okay, so when you say representation theory.
Representation theory of a quiver.
Oh, quiver representations.
Yes.
Oh yeah, so there's also, yes. So there is a bijection between, indecomposable representations, quiver representations of these algebras, and the cluster variables, except the initial cluster variables they kind of correspond to zero modules. So that's you have to add something called shifted projectives usually. And then the representation theory sees the cluster algebra completely. And this is in terms of tau tilting theory. I'm not sure if you're familiar with that. So tau tilting modules is modules which have no maximal modules such that home from M to tau M is 0. And so modules with the maximal modules, these properties correspond to clusters. And then the indecomposables will always be tau rigid. They will always satisfy, so they will correspond to cluster variables. And there's a whole very nice theory in from quiver representations, but yeah, I'm not gonna unfortunately talk about that in this class. Right, so that's finite type. And then I said we also understand the finite mutation type. I think this is quite miraculous. So how can you classify all quivers whose mutation class is finite? I mean, I think that's really beautiful. There is such a result, and the work is by Felixson, Shapiro, and Tumarkin, and they say that these are of finite mutation type if and only if you're in one of the following families. So first, if you have two vertices and however many arrows you want in the same direction, this is certainly of finite mutation type. I can mutate here or there. All it means is just gonna change the direction of the arrows. Nothing is happening. So that's obviously you only have finitely many quivers in this way. There's a whole family of quivers. Those that come from triangulations of surfaces. And so that's an important family as it comes up in this characterization. And this is the type of quivers we're going to talk about at the next lecture, triangulations of surfaces. There's these finite families coming from type E, the exceptional ones. So E6, 7, 8, that's the ones we saw on the previous slide. E6, 7, 8 tilde. Tilde just means tame, and this means I'm going to add a vertex at the appropriate spot to one of these ones from the previous slide. And there is E6, 7, 8 elliptical, I think, elliptic these are called. And again, it's one more vertex you add to the previous one. And so these have appeared previously in the literature in studying other things, so that was okay. And then in their classification, they also come up with these somehow new quivers, strange quivers, X6 and X7, which are finite mutation types still, which are not one of the above and sort of haven't really appeared anywhere else in the literature that they saw. And so if you're curious, they're not that scary looking. This is E6 and this is E7. They're indeed a finite mutation type, but none of sort of the techniques maybe from previous really work for them. These are, again, one think of them as exceptional. If you want to show something holds for finite mutation type quivers, these you would usually treat separately. And so this was like, the proof of this is quite involved. They do have to do a lot of cases. And I think they also do some computer calculations to help them compute things. All right. Oh, and speaking of computer calculations, this is perfect. So there's something called Keller's mutation applet. So if you go on Google and you search Keller's mutation applet, there's, for me, and I'm pretty sure for you as well, the first link, you click on it, and then there's a Bernard Keller's webpage there. And then he coded a program which allows you to build a quiver, and then add arrows and then start mutations. You would just click on the vertices. Once you're done building your quiver, you see it says you can add nodes. So if you were to click on the screen, it would add nodes. You would add arrows. So if you click on this add arrows button, and then you would click on vertex 1 and then on vertex 3, it would add an arrow from 1 to 3. If you wanted to add 2 arrows, you'd have to do click on 1 and 1 on 3 again, and it would add 2 arrows and so on. Delete nodes, freeze nodes, we didn't talk about that. You don't need that. And then after you're done, click done. And then once you click on any of the vertices here, it would mutate for you. So that's very nice. So this is what's on the web page. There's also one you can download on your computer. I tried doing that, but then I would need a Java and I didn't have time to install that. But it's not so bad. Once you download it, it actually allows you then to compute the cluster variables as well. So on the website, I think it only does the quiver mutations. If it actually compute the cluster variables for you, the mutations of the cluster variable, and it would actually simplify the expression for you as well. So you would get out Laurent polynomials. So it would already do the simplification, But eventually, okay, this is also has limited power, and these things grow very fast if you start with some wild quiver, many arrows. So eventually your computer will freeze, and that's okay once these expressions get too long. So just be aware. But this is very nice if you want to play around and, you know, check yourself, check your calculations. This I highly recommend it. Keller's mutation applet. All right, and sort of to close up, let me just say that so the generality that I gave you today is not the complete generality. There are various generalization of cluster algebras. Okay, there's a question in the chat. Will the presentation be available after lecture? Yes, I believe they will post the lecture notes on the web page of the class, of the school.
Yes, and I'm recording it, so probably video will be.
Yes, they will also be recording. Thank you. Yes, there are various generalizations of cluster algebra that come from these connections to other fields. So one is this skew-symmetrizable case that I tried to talk about before. So these, this would correspond to not the quiver Q, but sort of a valued quiver Q, where you can think of putting some values on the arrows. And the idea behind it is sort of you would have a different number of arrows, like you have different number of arrows coming out of a vertex for that arrow versus coming into the other vertex. And so these would correspond to the non-simply laced cases, for example, but then more generally you can do things. One can also introduce something called coefficients, so more data. And this is quite powerful, but we're not going to talk about that. And then there's a notion of mutations for the coefficients as well, and there's just more structure to it, more layers. There's also a notion of quantum cluster algebras where you introduce this quantum parameter Q as well. There's more generalized cluster algebras where you generalize the exchange relation. Maybe it's not a binomial relation anymore. Maybe it's more involved. And these have appeared as well. And there's recently the notion of something called the supercluster algebra. Okay, it's really not super in quotation marks. Super means that it's a Z2 graded algebra. And this has recently come up in relation to triangulations of surfaces. And the motivation for this comes from something called super higher Teichmüller theory, if you know what that is. And if not, that's fine. So, and then ... Okay, these are just the ones that came to my mind when I was writing up the notes. But there's a whole zoo of other algebras one can think about. Okay, and okay, next. Okay, and my very last slide. Okay, I'm almost done, I promise. So some more sort of applications. So one nice thing that happens is, okay, we had these cluster variables, and these cluster variables are Laurent polynomial in the xi's, and they're actually positive. So nice thing that happens if you specialize all the initial cluster variables to 1, let's say, then all the other cluster variables become positive integers because the denominator divides by 1, the numerator is some sort of integer. So you get integers, and so you get some really nice sequences you can get out in these ways. And so these are somehow nice connections to number theory. You get the Markov numbers in this way. You can easily get Fibonacci sequences. There's also something called the Somos sequences I believe from physics. And so other things like that. Recently, cluster algebras have been used to compute knot invariants. So again, you have a knot, you can associate a quiver to it, and there is some cluster variable you can do. And then once you specialize the values of the cluster variable to some other parameterize it, then you get like Alexander polynomials or Jones polynomials, so these famous knot invariants. Cluster algebra are also used to show something called the Molotnikov periodicity conjecture. This was also a very big result. So it's some sort of big equation that was conjectured to satisfy some periodicity properties, but it was really hard to work with. And indeed it did. And one can do so not so hard from cluster algebra theory. And then, for example, cross algebras from Grassmannians, which we're going to talk about in the next lecture, they can be used to understand something called KP equations. And these are some differential equations that can model, for example, shallow water waves, how waves propagate in shallow water. So again, something really seemingly unrelated, and yet it has the same combinatorics as these cluster algebras. So that's sort of the miraculous theory of cluster algebras, and it's really, really cool connections. All right, and that's it for today. So thank you very much for your attention, and any further questions?